Infants perform spontaneous limbs movements before mastering goal-directed actions like reaching. These early movements are thought to explore fundamental motion patterns, a crucial step in developing motor dexterity. We hypothesize that infants' spontaneous arm movements are not unconstrained explorations of all arm kinematics. Instead, they hold features that engage with key biomechanical forces, resulting in dynamically rich joint trajectories. We analyze the dynamic richness of infant upper limb movements using a multi-stage, automated process. First, 3D motion data from two different datasets was transformed from Cartesian to joint coordinates using a custom infant kinematic model. This allowed for detailed dynamic analyses at the joint level. Second, the data was segmented into individual motion sequences using an algorithm aligned with known infant movement characteristics. To quantify dynamic richness, we employed two metrics. First, the condition number, which measures how effectively inertial parameters are simultaneously excited, with one indicating uniform excitation. Second, the interquartile range, which quantifies the dispersion of each kinematic variable, indicating the range of values explored. However, a lack of comparative data hindered our ability to understand the extent of exploration in infant spontaneous behavior. To address this, we created two synthetic datasets. First, the excitatory set, designed to maximize dynamic excitation by optimizing the condition number. Second, the reaching-like set, optimized to resemble mature reaching movements by minimizing jerk between arm joint positions. These datasets provide lower and upper bounds for arm dynamics exploration. We identified two prominent dynamic features that clearly distinguish infant spontaneous arm movements from reaching-like motions. First, stable simultaneous excitation of all inertial parameters. Second, salient exploration of high acceleration regimes. By comparing infants' movements to these synthetic baselines, we isolated specific dynamic features emergent across individuals. Notably, these features also emerged in simulated excitatory motions, optimized using a trajectory metric common in robotics. This emergent exploration of dynamics is reproduced across different motion clusters. This suggests that beneath the variability of spontaneous motion, there is both structure and a salient search for arm dynamics. Our results demonstrate that both real and excitatory sets exhibit broader global coverage of joint kinematics compared to reaching-like motions. While all sets show variability, they differ in sensory-motor exploration coverage, as not all kinematic motions produce consistent patterns of arm dynamics exploration. These findings reveal that dynamic richness is an important feature of infant spontaneous movements, paving the way for future investigations into how this exploration contributes to the development of later skills such as reaching or manipulation.